Ariane 5 did not fail when it exploded. It failed when software from an older rocket entered a new one without its assumptions being tested again. On 4th of June 1996, Europe's new Ariane 5 launcher lifted off from Kourou in French Guiana. Its engines and boosters were working. For 30 seconds, the flight appeared normal. Then both inertial reference systems stopped providing usable guidance. The flight computer received diagnostic data and treated it as a genuine movement. It ordered an extreme course correction. The rocket turned sharply. Aerodynamic forces began tearing it apart. The safety system destroyed what remained. 4 scientific satellites vanished with it. The explosion was spectacular. The decision that caused it was almost invisible. Proven software had been trusted without proving that its hidden assumptions still applied. The usual explanation is simple. A number became too large, a software crashed, the rocket exploded. That is technically correct, but it makes the failure sound unpredictable. It was not. Ariane 5 had inherited parts of Ariane 4's navigation software. Ariane 4 had flown successfully for years. Reusing its software reduced costs and avoided unnecessary redesign. That was not irrational. But software is only proven inside the conditions it has survived. Ariane 5 created different conditions. The inherited assumptions were never fully tested against them. Before launch, the inertial reference system aligned the rocket's navigation platform. Once the rocket lifted off, that function was no longer needed. But the software kept it running for roughly 40 seconds into flight. That behaviour came from Ariane 4. Its countdown could be interrupted late. Restarting the full alignment process could take around 45 minutes. Keeping the function active allowed some launches to resume without losing their window. For Ariane 4, that made sense. Ariane 5 used a different preparation sequence. It did not need the feature. Yet the function remained because the software had already worked. The old code was not dangerous by itself. The danger was its hidden assumption that Ariane 5 would remain inside Ariane 4's limits. Ariane 5 accelerated horizontally much faster than Ariane 4. While the unnecessary function continued running, it calculated a value called horizontal bias. That value exceeded the expected range. The computer attempted to convert it from a 64-bit floating point number into a 16-bit signed integer. It tried to place a large value inside a smaller container. The value would not fit. The conversion produced an operand error. 7 similar variables had been identified. 4 were protected against this kind of failure. 3 were not. Horizontal bias was one of them. The decision reflected computer workload limits and analysis showing the values could not become dangerous. That analysis was valid for Ariane 4. It had not been recalculated using Ariane 5's trajectory. The rocket had changed. The numerical limit had not. Ariane 5 carried 2 inertial reference systems. One was active, the other was a backup, but both used the same hardware and software. Both encountered the same unexpected value. The backup failed first. The active unit failed during the next processing cycle. The flight computer tried to switch systems. Nothing remained to take over. This was redundancy against random hardware failure. It was not redundancy against a shared design error. 2 copies of the same assumption do not provide independence. They provide 2 routes to the same failure. When each processor encountered the exception, it shut itself down. That response was deliberate. The design assumed a serious exception probably meant faulty hardware. The healthy backup would continue. But the hardware was healthy. Both computers met the same condition their designers believed was impossible. Both obeyed their instructions. Both stopped. Before the active system shut down, it sent diagnostic information to the flight computer. The computer interpreted that bit pattern as navigation data. The numbers appeared to show a severe attitude error. The error did not exist, but the computer responded as though it did. It commanded the booster nozzles and main engine to make a violent correction. Ariane 5 pitched away from its path. Its angle of attack exceeded what the vehicle could survive. The structure began breaking apart. The automatic destruction system ended the flight. The rocket was not behaving randomly. It was responding correctly to meaningless data. One system reported that it had failed. Another mistook the report for instructions. The chain could have been reproduced before launch. Use the real inertial reference system. Feed it Ariane 5's predicted trajectory. The horizontal bias exceeds this limit. The first system stops. The second follows. The failure appears on the ground. But the actual inertial equipment was not included in the decisive end-to-end test. Its output was simulated instead. That made testing easier. It also removed the internal behaviour that caused the accident. The simulation produced the data engineers expected. It did not reproduce what the real equipment would do when Ariane 5 exceeded an Ariane 4 assumption. The test confirmed the model. It did not challenge the machine. After the accident, investigators reproduced the internal events through simulation and examination of the recovered systems. The rocket had already performed the missing test. It performed it once, in flight. The chain could have been broken several times. Stop the alignment function at liftoff. Protect the conversion. Reject diagnostic data. Use genuinely independent backup logic. But the last broad opportunity came before launch. Test the real navigation equipment against the real trajectory. That step would have exposed the unnecessary function, the overflowing value, and the common failure in both systems. The software did not need to be rewritten from scratch. Its assumptions needed to be examined. That was the missing work. Ariane 5 was not destroyed because engineers reused software. Reuse is often sensible. It was destroyed because previously successful software was treated as universally safe. A function designed for Ariane 4 remained active on Ariane 5. A value stayed unprotected because an older trajectory could never make it dangerous. Two identical systems were called redundant, despite sharing the same vulnerability. A simulation replaced the test, most likely to expose the problem. Each decision appeared defensible in isolation. Together, they created a launcher that lost both navigation systems because of software it did not need after liftoff. The explosion came later. The failure began when an old assumption entered a new machine and nobody forced it to prove it still belonged there. That is the failure chain.